Good morning, ladies and gentlemen. It'll be a quick video today, just sort of practicing what we've done so far throughout the unit. In fact, this is just kind of wrapping up the unit on differential equations. And I found two interesting, AP style questions that deal with these concepts of solving for particular general solutions and particular solutions. But you'll notice that these questions also involve a lot of the concepts from earlier in the year. So I'm just showing these problems to you as sort of an illustration that on the AP, any one problem that you're given is not going to focus on just one particular unit necessarily. They might draw from concepts that you learned throughout the year. All right, so you have to be able to sort of see the connections between what we learned in November to what we're learning now. All of this information is related and connected in one way or another. So anyway, we'll have plenty of time for reviewing for the AP anyway, and hopefully you'll be able to draw those connections a lot more quickly than maybe you will now. But let's start with just tackling a couple of problems. So it won't be a long video. All right. Anyway, so we're given a differential equation and we are provided with some axes, and we're sort of told a set of points that we want to draw the slope field for. All right, so part A, we're gonna go ahead and draw the slope field. Actually, I'm just gonna show you an example of like 3 points, and then the rest of the situation, actually, I'll show you 6 points. And the rest of the points, I mean, the process is exactly the same. All right, so my differential equation, I'm just gonna write it down here. So we have it, dy over dx is equal to negative 2x over y. So basically, that's the equation that's going to generate my slopes for any particular point. So let's take the points, 3 points in the top row there. The coordinates are negative 1, 2, 0, 2, and 1, 2. And so the idea is I'm going to take those points, plug them into my slope equation, and I'll ultimately get a slope. So when I plug x equals negative 1 and y equals 2 into the differential equation, I ultimately get 1. When I plug 0, 2 into the differential equation, I get 0. And when I plug 1, 2 into the differential equation, I get negative 1. So I use that information on the graph to draw the slopes. So at the point negative 1, 2, there will be a slope of 1. And just do the best you can to draw a slope of 1. At the point 0, 2, there will be a slope of 0. And of course, we know that means a horizontal line. And at the point 1, 2, there will be a slope of negative 1. Okay, so that's the slope field thus far. Obviously, you would continue on for all the other points. I'm going to go down to that row on the x-axis. So those are the points 0, those are the points negative 1, 0, 0, 0, and 1, 0. Now, when I plug those points into the differential equation, you'll notice that since y is 0 for all these points, that means there's a 0 in the denominator. So actually, dy dx is undefined for all 3 of these points. And now when we're referring to a slope, an undefined slope, well, what does that mean graphically? What does that slope look like? Well, an undefined slope is a slope of a vertical line. So if we go to the point negative 1, 0, on the slope field, if you get a slope that's undefined, you're going to draw a vertical line. So you're going to do that at negative 1, 0, 0, 0, and 1, 0. Okay. All right, and I'm going to leave the rest of the points up to you. I think you get the idea at this point. Really, it's part B that now brings some older material back into the mix. So y equals f of x is going to be the particular solution to our differential equation with the initial condition f of 1 equals -1. What they want us to do in part B is to write an expression for the tangent line to the graph at 1, -1, and use it to approximate f of 1.1. All right, so this goes back to the idea of linear approximation. Just remember, the idea is when we have a curve, we can write the equation to the tangent line, to the line tangent to the curve at that particular point by just knowing the point on the curve and then also the slope of that tangent line. All right, if we know that information, then we have all the information we need to write the equation of the tangent line at that particular point. All right, so here's part B. So let's go ahead. In this case, I'm dealing with the point 1, -1. So I'm going to use that to determine the slope. I want the slope at the point 1, -1. Well, how do I determine the slope? Well, that's exactly what the differential equation gives us. So the slope at 1, -1 is the same thing as saying, well, what's the value of the differential equation at 1, -1? And of course, when we plug 1, -1 into this differential equation, you get a slope of 2. All right, so now putting the pieces together, so we have the point 1, -1, we have a slope of 2. I can use point slope form to write the equation of the tangent line as 2 times x minus 1 is equal to y plus 1. Now, when I'm writing a linear approximation, I take my tangent line equation and I solve it for y. So my linear approximation function will equal 2 times x minus 1 minus 1. Okay, you can see that all this is taking this equation and solve for y. And y is going to equal your linear approximation function. All right, now the idea is the function f of x, the actual particular solution, can be approximated by this linear approximation that we found for points that are near x equals 1, right? Once we go very far away from the point that we're estimating, that we're approximating at, then the linear approximation gets worse and worse and worse. But we can use this linear approximation to approximate values of the function near x equals a. So in this case, I'll just rewrite the linear approximation. So our f of x is going to be approximately equal to L of x for points near x equals 1. So now the goal of the problem, scrolling back up, the goal of the problem is to use this to approximate f of 1.1. All right, f of 1.1 is going to be approximately equal to L of 1.1. And L of 1.1 is equal to 2 times, well, 1.1 minus 1 is just 0.1, and all that minus 1. And we get 0.8. Sorry, negative 0.8, of course. All right, and so that's part B. So the approximate value of the function f at x equals 1.1 is negative 0.8. All right, now part C is something we're more familiar with in from recent lessons. Is we want to use our differential equation to find the particular solution given this initial condition. Okay, there's a little bit of something that we have to be careful of here. All right, just making sure I have enough room. So I'm going to start with the differential equation, dy dx me just make sure I have it right, is negative 2x over y. Okay. And I'm told that f of 1 equals negative 1. Okay. Now I'm going to use this information to find the actual particular solution of this function, given this initial condition. All right, the first thing I'll do is I will separate my differentials. So the good thing is this is a separable differential equation, so I don't actually really have to rely on a slope field. I can separate and integrate. So I'm going to have integral of y dy is equal to negative 2 times the integral of x dx. Okay. Integrating, I have y squared over 2 is equal to negative x squared plus c. Now, you'll notice I'm sort of skipping some steps. There are things that canceled out here. I'm not going into great detail because at this point, hopefully you're able to figure out why that negative 2 is gone, and actually it's just become negative 1. So if you're not sure, just sort of go through the steps yourself and think about it. This is definitely something at this point you should be able to figure out. So at this point, actually, I can use my initial condition. I actually recommend typically to use your initial condition as early as possible. So remember, we were told that the point 1, negative 1 exists on this curve. So I'm going to plug that in and solve for c. So I have negative 1, that quantity squared over 2 is equal to negative of 1 squared plus c. And that implies that c is equal to 3/2. This is c. All right, I didn't go through the algebra, but please go for it. Do the algebra on your own. All right, so now that's not the final answer. I'm going to go back to my step that I was at. So we were at this step. We've solved for c, and so now I'm going to plug that value of c in. I have y squared over 2 is equal to negative x squared plus 3/2. Remember, the ultimate goal here is that I need to solve for y. So I want to isolate y. So I'm going to multiply both sides by 2. And I have y squared is equal to negative 2x squared plus 3. And I still have an isolated y. I have to get rid of that exponent. So I'm going to apply radical to both sides. And I will have y is equal to plus or minus radical negative 2x squared plus 3. All right, now the issue is I have to specify which branch I'm actually using. There's a positive branch, there's a negative branch. Based on our initial condition, which one do you think we're using? So I'll let you think about it for a moment. But our initial condition, of course, is, once again, we have the point 1 comma negative 1. Well, the fact is, y is negative here. And so the only way, if we have a function that looks something like this with a radical, the only way for y to be negative is if we use the negative branch. So our final answer is actually going to be y equals radical negative 2x squared plus 3. Oh, sorry. I totally forgot that we're using the negative branch, right? That was the whole point of what I just said. So yeah, we need that negative in front of the radical in order for our y value to be negative when we plug in an x value in the domain of this expression, of this function. All right, there we have it. Those are parts A, B, and C. It would actually be interesting, I'm not going to do it right now, but be interesting to see, and this, by the way, is your function f of x. It would be interesting to see what you get when you plug 1.1 into this function and to see, is it approximately, what did we get for our approximation? Negative 0.8. You should check it out. Is it approximately negative 0.8? I would guess it's pretty close. All right, moving on. I saw this problem on AP Classroom, and I thought it was pretty interesting. So I wanted to go through it in detail. So we're given this graph. Notice that this is the graph of the derivative of f, and it's not the graph of f. So you have to really be careful when you're going through the AP. When you're given a graph, make sure that you read any little notes or descriptions of what the graph represents, because they could give you the original graph, they could give you the derivative graph, they could even give you the second derivative graph. So we need to be alert to what exactly it is that they're giving us. All right, so we're given the graph of f prime. We're told that the domain of the original function is all x values between 0 and 2, and we're told that f of 1 is equal to 0. We're told next to write an expression for f of x in terms of x. All right, so basically this is a fancy way of saying find the particular solution given this differential equation, right? Because really, what are we told? Or what are we given? We're given dy dx. We're given the f prime function, right? And this is actually, our derivative is going to be written as a piecewise function. From 0 to 1, this is the line y equals x. So I will say that dy dx is equal to x for x equals 0 to 1. And for for 1 to 2, this is the line negative x plus 2. All right, you can find that, of course, by determining the slope. You're given 2 points, 1, 1, and 2, 0. So you can find the slope. You know a point that exists. You can use point slope form and then just sort of isolate y to get the slope intercept form. So you have dy dx is equal to negative x plus 2 for the x values between 1 and 2. Notice that I decided to include 1 in this lower branch over here. It really shouldn't make a difference, or in fact, it doesn't make a difference when we actually, yeah, this is the derivative function, and it is constant, right? So it is continuous. The derivative itself is continuous. It's defined for all values between 0 and 2. So I had to choose one of these two branches, but you'll notice it doesn't matter which one I choose because the upper branch evaluated at 1 is 1, and the lower branch evaluated at 1 is also 1. So it really doesn't matter which one you choose. Okay. Now, moving forward, we want to find f of x. Well, I need to solve my differential equation in order to do so. And it turns out that since my differential equation is a piecewise function, I actually have to solve two differential equations, one for each branch that we're given. All right, so actually, as it turns out, that my original function is also going to be piecewise. It's going to be piecewise for the same little domains. Okay, but what I'll do is just set up two differential equations, dy dx equals x, and then I'll set up dy dx is equal to, what was the other one? Negative x plus 2. And at this point, it's just a matter of solving, separating and integrating like we have done many times before this. I'm going to skip the steps. This ends up giving you y is equal to x squared over 2 plus c1. This ends up giving you y is equal to negative x squared over 2 plus 2x plus c2. I am making sure that these constants have subscripts because they are different numbers, or they are potentially different numbers. And so I want to treat them separately. The idea is they're both going to have to satisfy the initial condition, which is that f of 1 is equal to 0, right? It turns out that the initial condition they give us is at this point 1, this value x equals 1, which happens to be sort of on both branches. So we do need to evaluate the initial condition at both branches in order for us to get an official final answer. So I'm going to go ahead and plug in our initial condition, which is that f of 1 is equal to 0. So 0 is equal to 1 squared over 2 plus c1. This tells us that c1 is equal to negative 1/2. Similarly, 0 is equal to negative quantity of 1 squared over 2 plus 2 times 1 plus c2. And this tells us that c2 is equal to negative 3/2. All right, so going up here, I don't know if I gave myself enough space, so I'm just going to rewrite it down here. So our final answer for f of x will be x squared over 2 minus 1/2 for the values between 0 and 1, not including 1, and negative x squared over 2 plus 2x minus 3/2 between 1 and 2. Now, one thing you will want to check. I guess they don't tell you. Yeah, so since the function is differentiable between 0 and 2, and we know it's differentiable because, I mean, we're looking at the derivative function right here. This is the derivative function. Since this function is differentiable, you want to make sure that it's continuous. So you want to just sort of confirm that your values of C1 and C2 are correct by evaluating the function at 1 for both branches. And if you do that, you should get the same y value. And I believe it turns out that you should get your initial condition, right? That f of 1 is equal to 0. So, I mean, a quick check shows you that if you plug 1 into the top branch, you get 0. That checks out. A little bit of a longer, but just, you know, still a fairly quick check. If you plug 1 into this bottom branch, you're also going to get 0. So that basically allows us to confirm that our initial condition matches for whichever branch we use. And that means that our function is going to be continuous. All right, ladies and gentlemen, that's all I wanted to share with you. I just thought those were two sort of interesting, maybe a little bit more intensive type problems dealing with the concepts, the recent concepts. So I hope you enjoyed. I hope this was helpful. I'll be posting homework, and just have a great day. All right.